Okay, so good to introduce you, Ahmed. So Ahmed Taha is a CS Ph.D. student at the University of Maryland, College Park, under the supervision of Professor Larry S. Davis and Abhinav Shrivastava. His research focuses on deep metric learning, representation learning, and visualization. Ahmed is graduating in spring 2021, and he is seeking a postdoc starting summer, fall 2021. And yeah, you can go ahead and start.
Okay, thanks Nathaniel for having me, and thanks everyone for coming to my talk. I am Ahmed Taha, a PhD student at University of Maryland. Today I will present my upcoming CVPR paper, Knowledge Evolution in Neural Networks. So deep learning has a lot of open and solved problems. One of these problems is how to train a deep network on a relatively small dataset. The knowledge evolution paper tackles this question and shows how to boost performance on small datasets while reducing the inference cost. Knowledge evolution is important not only to boost performance, but also to reduce the computational cost of training neural networks. Training a neural network is expensive because of two factors, the deep architecture and the large training dataset. To reduce the training cost, we have to tackle at least one of these two factors. Small datasets provides an opportunity to reduce training time. A single epoch on ImageNet is equivalent to 1,000 epochs on Flower 102 and 200 epochs on CUP 200. Thus, if we train a given network for a fixed number of epochs, training on Flower 102 is 1,000 times cheaper than ImageNet. Reducing the architecture size is another opportunity to reduce the training cost. The lottery ticket hypothesis literature tries to find a sparse subnetwork, as you can see here on the right-hand side, that can be trained to similar performance as a dense network. While this is a promising research direction, finding these sparse network is not straightforward. Even when we find these sparse networks, training them remains difficult because they require both special hardware and software to support such sparse connectivity. Thus, it is hard to quantify the benefit of reducing the size of deep architectures. In a high level, both the lottery ticket hypothesis and knowledge evolution aim to reduce the training cost. While the lottery ticket aims to reduce the size of the network, the knowledge evolution aims to reduce the size of training data. Before going into technical details, this animation presents the core idea of knowledge evolution. The first step of knowledge evolution is to split a neural network, as you can see here, into two. This network can be like ResNet 50. You split it into two parts. I will explain in the following slides how to do the splitting. But for now, let's just think that the network is divided into two parts, the blue part and the gray part. At generation 0 and 0, the whole network is randomly initialized, so its performance is low, as you can see on the y-axis. Now we train our network. This is your regular training procedure, nothing special so far. After training the network, this becomes the first generation and the network performance increases. Now, in knowledge evolution, we randomly reinitialize the gray part of the network, this part here, okay? This means we throw away part of what we have learned in order to reinitialize the gray part again. Then we retrain the network again. This becomes the second generation. We iteratively repeat this process to boost the network performance. The next slide explains how we split the network into two parts. So we propose two different splitting techniques. Both techniques use a binary mask M to outline the two parts of the network. So we call the blue part the fit hypothesis, and while the gray part is called the reset hypothesis. The first splitting technique is called Wells. This technique randomly initializes the network through its weights as shown on the left-hand side. The size of the blue fit hypothesis depends on a split rate, which is a hyperparameter. While it is possible to split the network regularly, as shown on the right-hand side, by default, Wells is a random, irregular splitting technique. This allows Wells to support any architecture without making any assumption. The second splitting technique is called Wells. It's called Wells because it splits the network using kernel granularity. It is tailored for CNNs. For example, on the left-hand side, we show a toy convolution filter F with 3 input channels and 4 output channels. This toy filter has 12 2D kernels. This pi can be like, for example, a 3 by 3 kernel. On the center here, we show how to apply CALs on a toy residual network. Giving a split rate, say 50%, we split the network such that the fit hypothesis in blue includes the top 50% kernels inside the top 50% filters. Please note that the fit hypothesis in blue here is a slim network that can be extracted from the dense network N to perform inference efficiently. Once the fit and reset hypotheses are outlined, we train the whole network for multiple generations. To evolve the knowledge inside the fit hypothesis, we reinitialize the reset hypothesis after every generation. The knowledge evolution training approach is simple. It has 2 main parts. The first part outlines the fit and the reset hypothesis using the binary mask M, as shown on the left-hand side. Once the mask is defined, we simply train the network for multiple generations and reinitialize the reset hypothesis after every generation, as shown on the right-hand side. In the next slides, I will present the intuitions behind knowledge evolution, but for now, does anyone has questions about the training approach?
So I have a quick question.
Yeah, sure.
Does the so the part that you're throwing away, is it a different one at each step? It's the same at each step, right?
Yes, yes. So for example, this mask here set this part as a reset hypothesis because there are zeros here, so it is the same part. Yeah.
Got it. Thank you.
In the paper, I try to explore this in the appendix, but I don't. Maybe at the end we can go over this. I have a slide for it, but it's like an extra slide.
Got it. If anyone has questions, please type them in chat and I'll ask them.
Okay. So I will move forward and feel free to interrupt me at any time to ask your question. So I will present 2 intuitions to explain why knowledge evolution work. So the first intuition comes from dropout. Dropout randomly drops neurons during training. This encourages these blue neurons to rely less on each other and to learn independent representation. In knowledge evolution, we drop the reset hypothesis after every generation. This encourages the fit hypothesis to rely less on the reset hypothesis and to learn an independent representation. We validate this intuition by evaluating the performance of the blue slim fit hypothesis across generation. We observe that the performance of the fit hypothesis increases as the number of generations increases. The second intuition comes from the residual networks. ResNets set the default mapping between consecutive layers to the identity, as you can see here. Yet from a different perspective, ResNets enable a zero mapping in some subnetworks like these residual links without limiting the network's capacity. Similarly, KE enables a zero mapping inside the reset hypothesis by reusing the fit hypothesis across generations. At the first generation, after the first generation N1, the fit hypothesis is always closer to convergence compared to the reset hypothesis, which is randomly initialized. Thus, we encourage new generations to evolve the previous generation's knowledge inside the fit hypothesis and to suppress the randomly initialized reset hypothesis. We validate this intuition by measuring the mean absolute value inside both hypotheses. we observe that the fit hypothesis and the reset hypothesis have a comparable mean value at the first generation and 1. However, as the number of generations increases, the mean absolute value inside the fit hypothesis increases while the reset hypothesis decreases. This supports our claims that Ke promotes a zero mapping inside the reset hypothesis. Now, Ke makes no assumption about the training settings. So it doesn't matter if you are doing supervised or unsupervised learning. Also, Ke is oblivious to the loss function used to train the network. Accordingly, we evaluate Ke using both retrieval and classification networks. We leverage triplet loss to train retrieval networks and cross entropy to train classification networks. We evaluate knowledge evolution on 5 small data sets and 2 different architectures. The performance of deep networks on a small data set is studied intensively using the classification task. Thus, the classification task provides a rigorous performance benchmark. This table presents quantitative classification evaluation using ResNet 18 and 5 different data sets. In this experiment, we use Kel's splitting. We applied knowledge evolution on both on top of the vanilla cross entropy label smoothing regularizer and CSKD regularizer. Ke is flexible and boosts performance on each baseline. The third generation outperforms the first generation on all datasets. After reaching a peak, for example here, the knowledge evolution performance fluctuates. Thus, if the third generation outperforms the 10th generation, this indicates that Ke reached its peak. Similarly, we evaluate Ke using DenseNet. Again, Ke achieves significant improvement margins. This table highlights the improvement margin achieved by knowledge evolution for both the dense and the slim fit hypothesis. This table also highlights the inference cost saving achieved by knowledge evolution. And this table shows performance on 3 datasets and 3 architecture in 3 different sections. So I will explain the first section only to illustrate how to read these numbers. So the first section shows a quantitative evaluation using VGG11 on CUP200 dataset. In this experiment, we use a split rate 0.5. So the first row shows the performance and the inference cost of the dense network N, while the second row shows the performance and the inference cost of the slim fit hypothesis H. At the first generation, the dense network N achieves around 63% accuracy, while the slim H achieved like almost 0% accuracy. After 10 generations, both N and H achieves approximately 68% accuracy. Now, this is an absolute 5% improvement margin over the first dense generation, which is 63 point something. It is worth noting that the slim network H is achieving comparable performance as the dense network, but with a relative 74% reduction in inference cost. This table presents quantitative retrieval evaluation. We evaluate knowledge evolution using 2 standard retrieval dataset and 2 standard retrieval architecture. Ke boosts recall at 1 by an absolute 5% on CUP200 and 27% on Stanford Cars dataset. Retrieval network literature never trains this architecture from scratch. This explains why we have a single baseline in this table. Again, for retrieval networks, knowledge evolution delivers both a slim and a dense network. This figure shows the performance of the dense network on the right-hand side and the slim fit hypothesis on the right-hand side. So at the first generation, the dense network recall at 1 is 10%, while the recall at 1 of the slim network is around 5%. As the number of generation increases, both the dense and the network and the dense and the slim network performance increases. This is the same experiment, but on the Stanford CARS dataset. Again, the performance of both the dense network and the fit hypothesis increases as the number of generation increases. Similar to classification network, this table highlights both improvement margin and the cost reduction achieved by knowledge evolution for retrieval networks. In the following slides, I will present some application studies to understand the strengths and weaknesses of knowledge evolution. For example, in this figure, we compare Wells and Kells technique. These are the two splitting techniques that we proposed. Only Wells can deliver a slim network as shown on the right-hand side. However, both Kells and Wells achieve comparable performance. This is promising because Wells can be applied to any neural network. In this figure, we highlight the trade-offs of the split rate SR. Both small and a large split rate are used, and both of them will boost the performance of the dense network as shown on the left-hand side. However, a small split rate, say 0.5, will lead to a slim fit hypothesis with an inferior performance here. The fit hypothesis with a split rate 0.8 achieves comparable performance to the dense network N. However, the fit hypothesis with a split rate 0.5 lags in terms of performance significantly. Please note that with a split rate 0.5, this fit hypothesis is approximately quarter of the GoogleNet. Okay, so in deep learning, we assume that more training data leads to a better accuracy. However, the knowledge evolution improvement margins contradict this assumption. For example, the Flower 102 dataset is a much smaller dataset compared to the CUP 200, yet the improvement margin is over 20% for the Flower 02 as shown by the blue curve, while it is less than 10% for CUP 200 as shown by the red curve. We claim that the improvement margins depend not only on the dataset size, but also on the dataset simplicity. To evaluate our claim, we quantify the simplicity of our 5 datasets through a pre-trained network. The ImageNet weights in a pre-trained network mitigate the negative impact of a small dataset. We leverage the performance of each dataset as a surrogate for its simplicity. High accuracy indicates a simple dataset. In this figure, the x-axis denotes the accuracy on the pre-trained network, and the y-axis denotes the Ka improvement margin. For example, the Flower 102 has like around 90% accuracy on the pre-trained network, and Ka achieves like 14% improvement margin after 10 generations. We found a strong positive correlation with R equal 0.85. This experiment indicates that the dataset size is no longer the dominant factor that controls the performance of a randomly initialized network on a relatively small dataset. This result is intuitive too. Indeed, humans can generalize from a small sample size. However, this happens when the task is simple, such as recognizing dogs versus cars. However, when the task gets complicated, such as recognizing different breeds of dogs, either a knowledge expert or a large sample size is required. We evaluate knowledge evolution. In the previous experiments, we evaluate knowledge evolution on mainly small datasets. However, Ka works for large datasets as well. This table shows the performance of the dense N and the slim H networks when evaluating knowledge evolution on ImageNet and post ResNet 34 and ResNet 50. As you can see, Ka boosts both the dense network and the slim fit hypothesis as the number of generation increases. In this experiment, I applied knowledge evolution for 5 generations only. If I had access to more GPUs, I would have evaluated Ka with more generation and with different hyperparameters, for example, different split rates. Before concluding my talk, I want to say that the reason I come up with knowledge evolution is that I was trying to train retrieval networks from scratch. I'm interested in retrieval networks because its output, the feature embedding. This figure shows the feature embedding and how different classes relates to each other. I think feature embedding is very interesting, and that's why I'm interested in topics like retrieval network, representation learning, and self-supervised learning. For those who share the same interest, these are two of my recent papers. The common factor between this paper is feature embedding. When I report classification evaluation, I'm only doing it to get the paper accepted. However, every paper starts by trying to solve a problem related to feature embedding. If you find this paper interesting and you want me to give another presentation, I will be glad to do so. Finally, I want to thank you again for having me today, and please let me know if you have any questions.
Thank you, Ahmed.
Okay, thank you.
Very good talk.
you.
Yeah, so for anyone that has any questions, you can directly unmute yourself, I believe, and you can ask them. Okay. Wait, Fred is clapping. Oh, I thought it was a question.
I actually have a slide here where, yep. So one of the questions you asked about is, do I change the reset hypothesis across generation or not?
Mm-hmm.
So in this experiment, I tried to change it. Like this Wells is when you don't change it, and Wells random is basically you change it between generations. And
which lines are, oh, the pointed lines are, the dotted lines
yes,
are the ones. Okay.
yes,
So there's a big gap, yeah.
yes, but this only when you have a small split rate. As when you have a big split rate, this margin diminishes, because basically if you already have,
you're deleting the network basically.
yes, so yes, with a small learning rate you are deleting the network, while with a big with a big split rate,
Mm-hmm.
you almost have the same network again, because like the probability is like of having the same weight in two consecutive network is like the split rate square. So
Mm-hmm.
if the split rate is 0.8, the probability is 0.8 that you will not, like, while you intentionally want to randomly reinitialize, you don't actually do so, because you basically, the whole network is on the fit hypothesis. Okay, so yeah.
Makes sense. Yeah, this is interesting. Thank you, yeah, for that answer. Are there any other splitting methods that you would have thought about?
We have here like so I was mainly focusing on the operation used in CNNs. Okay, so I support like fully connected layers, convolution layers, and this is here on how to support concatenation layer. So it is not, yeah. So I think this will, as long as whatever your architecture, as long as you have this kind of operation, you can just basically use my layers.
Okay, I got it.
Yeah, but yes, it is. It would be interesting to try to think about more splitting techniques for different, like maybe transformers. This one thing was mentioned during the rebuttal.
Mm-hmm.
Two different reviewer like asked for. So it is interesting to do this for transformers as well. However, transformers and computer vision tend to be expensive, and so I need a lot of GPUs to be able to deliver such experiments.
Makes sense. Well, thank you so much.
Okay, thank you. Thank you for having me today. Okay, thank you.
Yeah, no problem. So now we're going to our next speaker, Kuniaki.
I will stop sharing my screen.
Yeah, and I have to basically promote Kuniaki to co-host. There we go. All right. Can you share your screen, Kuniaki?
Yeah.
All right. Okay, so let me introduce you. Kuniaki is a PhD student advised by Professor Kate Saenko here at BU and joined the IVC group in 2018. He received his master's degree from the University of Tokyo, where he worked on domain adaptation with Professor Tatsuya Harada and Dr. Yoshitaka Ushiku. His research interest focuses on computer vision and machine learning. Currently, he is working on domain adaptation for computer vision. Yep, please take it away.
Yeah, thanks for the introduction. I'm Kuniaki Saito, a PhD student advised by Kate. So today, I'd like to talk about our recent work, OVANet, one versus all network for universal domain adaptation. So in this work, we tackled one of the problem of dataset bias. And the dataset bias problem is one of the issues in various image recognition tasks. So a model trained on a specific domain may not generalize well to the novel target domain when the target domain has different characteristics from the training domain. And the dataset bias issue can happen in image classification, semantic segmentation, object detection, or maybe in other tasks too. And many researches have been done to handle this problem. Domain adaptation is one of the fields that tackles dataset bias issue. And the goal of domain adaptation is to transfer the knowledge from label-rich domain to a label-limited domain, which is called target. And the goal is to reduce annotation cost in the target domain. Now, one popular task is unsupervised closed set domain adaptation, where we have some labeled source samples and we have unlabeled target samples. An assumption here is that the target domain has the same categories as the source domain. But this assumption is not always realistic since the target domain is unlabeled domain. So the target domain may have some categories absent in the source, or maybe some categories in the source are absent in the target. So the category overlap may not be complete in many cases. And many researchers have tackled different settings of category overlap. So the closed set domain adaptation assumes the complete overlap of categories between source and target. In partial domain adaptation, the categories of target are the subset of source. And in open set domain adaptation, we assume the existence of some unknown categories in the target, which are not present in source. And in open set domain adaptation, we need to classify the samples of the shared categories into the correct class. And we also need to reject unknown target samples as unknown. An open partial domain adaptation is a combination of open set domain adaptation and partial domain adaptation. And many methods have been developed for each category shift, and they are tailored for each shift. But the true difficulty is that we don't know which shift is happening in the target domain, since it is an unlabeled domain. So we don't know how the categories are shared with source. So given this difficulty, the task of universal domain adaptation is proposed. So where we needed to solve the domain shift problem without knowing the category shift. The method needed to work well on any kind of shift here. And the main difficulty in this task is how to reject unknown target samples. The difficulty is common with open set domain adaptation. So since there are no supervision for the unknown target samples, it's hard to build a classifier that can identify unknown target samples. We don't have any labeled target samples, and we don't know how many target samples come from unknown classes. And existing approaches use some form of confidence thresholding. So they first compute some confidence score for the classification output and decide known or unknown by a manually set threshold. So if the confidence score is lower than the threshold, the sample is probably from unknown class. And they decided the threshold by using validation or using the ratio of unknown samples. But this, the approaches clearly violate the assumption of task that the target domain is unlabeled domain, and we don't know how many target samples are unknown. So in this work, we propose a method that can build a threshold without using any validation or ratio of unknown target samples. Okay, let me explain our key idea. Our key idea is that the distance between classes can be a good threshold to decide known or unknown. So using source samples, we can estimate the margin from the nearest class for each class. So in this figure, this is a margin. And this margin can be a good threshold to reject unknown samples. This is our key intuition. And to run the margin, we propose to train one versus all classifier for each class. So in this case, there are 4 source classes. So we train 4 one versus all classifiers. So this one decides car or others. And this classifier decides truck or others. And if an input sample is decided as unknown by all one versus all classifiers, the sample is probably from unknown class. So how do we actually train the classifiers? So we train C1 versus all classifiers, where C is the number of source classes, and we aim to run the margin from the nearest negative samples. So one option to train the classifiers given an input is just train all of them. So for each input, there is one corresponding positive classifier. And all other classifiers are kind of negative classifiers. So they needed to say the input sample is negative. And orange one needed to say the input sample is positive. We can just train the model to recognize the input that way. But if we propagate the training signal for all classifiers, the classifiers, the nearest negative classifier, so the black dot one, will not be updated much. And also, the far away negative classifier, so this one, will not run the margin from the nearest negative samples, because the input sample is not clearly the nearest negative for this classifier. So it's not a good way to train the one versus all classifiers. So to solve the issue, we train the 2 classifiers, a positive and the nearest negative classifier. So orange one is trying to do the input is negative, and the black dot one runs to say this sample is the nearest negative, and the far away classifier is not updated. So in this way, the classifiers will effectively run the margin from different classes. Okay, let me explain the detail of training. So first, each source sample, we have one positive class classifier. So the input here has class 0. So the corresponding class is updated to say the sample is from positive class. We can just compute the classification loss using cross entropy. Then To train the negative side, we need to pick the nearest negative class. So we can pick the classifier from these C-1 classifiers. So to pick the nearest negative, we can just check the score of output, because the score shows the probability of positive. So if the score is high, the sample is near to the classifier. Then after identifying the nearest negative, we can compute the classification loss to say the sample is negative. So overall, we pick 2 classifiers for each input to train the model. Does anyone have any questions so far?
If you have questions, you can directly unmute yourself, by the way.
Okay, then I will move. So far, I have explained how to train open set classifier using source samples. And after training, we still need to adapt the classifier to the target domain. Because the predictions of the classifier for the target can be ambiguous, because the target data has different characteristics from the source. So we needed to train the model to separate target samples from the decision boundary of open set classification. Yeah, so to achieve it, we simply do entropy minimization with respect to the open set classifier. The output of open set classifier shows the confidence of known or unknown decision. Then we increase the confidence by performing entropy minimization for the target sample. Okay, let me summarize the overall training process. So we train the open set classifier using source samples, and we adapt it to the target domain using entropy minimization. And during training on source samples, we also train the closed set classifier that classifies samples into known categories. And the overall objective consists of source loss, classification loss for source, and open set loss for source, and adaptation loss for the target. And where we have only one hyperparameter unique to this method. And in the test phase, the closed set classifier is used to identify which sample is the nearest known class. And we decide known or unknown by using open set classifier's output for the corresponding class. So this is a methodological comparison with other methods. So our method has only one hyperparameter unique to our method, whereas existing methods have many hyperparameters to tune. And the threshold to reject unknown sample is decided by validation or some heuristic decision, or using the number of unknown target samples. But our method runs the threshold by using the relationship between source categories. So we evaluated our method on diverse datasets, which have different number of classes. So Office has 31 classes with 3 domains. Office Form has 65 classes with 4 domains, and Visitor has evaluate synthetic to real adaptation with 12 classes, and DomainNet has 345 classes, which is the largest dataset for domain adaptation. So to see the robustness to various settings, we evaluate on various datasets and various settings of universal domain adaptation. Okay, first, let's take a look at the robustness to the number of unknown target samples. So here, we used Office dataset, and we pick 10 classes as known classes, and this is shared with target. And we vary the number of unknown classes. So our method consistently shows better or comparable performance to the baselines for different number of unknown classes. So the x-axis shows the number of unknown classes in the target, and left and right one shows performance on different scenarios. Our method shows consistently good performance, but baseline dance selects a threshold in a heuristic way, and ROS selects the threshold by assuming specific number of unknown target samples. So they are not very robust to the different number of unknown samples, but our method shows very stable performance. And the trend was similar in other datasets. So for BizDA and DomainNet dataset, our method outperforms other methods. Pitch tune the threshold or hyperparameters for each dataset, but our method doesn't change the hyperparameter across different settings, but outperforms the baselines. So from these results, we can say our method is widely effective with no need to manually tune hyperparameter. And here we analyze our method by plotting the frequency of open set classifiers output. So we wanted to analyze how the unknown and known samples are separated by our open set classification output. So the red one shows the value of known samples, and blue one shows that of unknown samples. So this baseline, which sets the threshold heuristic way, and the thresholds is not optimal, so it fails to reject many unknown samples. But in our method, this graph shows our method without entropy minimization. So it simply trained a model using source samples. And our method correctly set the threshold by using the relationship between source samples. Many of unknown target samples are correctly classified. And applying open set entropy minimization further enhance the separation from between known and unknown instances. Okay, finally, we did aberration study for our proposed two modules, which select hard negative samples to train open set classifier and entropy minimization. So the rest one shows H-score, which considers a trade-off between known class accuracy and unknown class rejection accuracy. So it's kind of accuracy, overall accuracy. And the rest one shows the accuracy of rejecting unknown samples. So using the hard negative sampling clearly improved performance in both metric. It's because the sampling improves the accuracy to reject unknown target samples, as the right graph shows. And the gap in DomainNet is much larger than other datasets. This is because the dataset has much larger number of classes. So if many classes are present, there are many useless classes to train open set classifier. So it is necessary to select suitable hard negative samples. And applying open set entropy minimization also consistently improves the performance. Okay, so in summary, we have proposed one versus all classifier training for universal domain adaptation. We proposed 2 modules to achieve our idea. One is hard negative classifier sampling and open set entropy minimization to adapt it to the target domain. And the effectiveness for universal domain adaptation is widely shown for different kinds of data sets. And aberration shows the effectiveness of our proposed 2 modules. Thanks for your attention. Any question?
Thank you, Kuniaki, for presenting. Does anyone have any questions? Okay. So, yep, if you have any outstanding questions for our presenters, please feel free to email me or email them. If you want to meet with any of our presenters today, they might have some time, so email me and we can try to set that up. Yeah. Thank you so much for attending and have a nice Monday, everyone.